Hello there, Mr. Sutton with the AB Calculus 6-1 homework solutions on basic differential equations. On this problem, I want the general solution for this differential equation. So basically, I'm just taking the antiderivative, going from left to right. This bumps up to a 2 for an exponent. Dividing by that, we've got 4x squared, and then minus 7x, and then plus c. On this problem, we want the general solution for this differential equation. That just means they want the general antiderivative with the plus c thrown in. So antiderivative of negative cosine of x is going to be negative sine of x plus c. For this problem, they want the general solution to this differential equation. So we'll start by taking the antiderivative. That's going to be 6 ln absolute value of x minus 2, all of that plus c. But we want to eliminate that ambiguity here with the absolute value. So we look up here where they gave us the condition that x is less than 2. Well, if x is less than 2, then that means we're going to have negative numbers, whatever x values we plug in, inside this absolute value. So the whole x minus 2 expression here is going to come out negative with x values that are lower than 2. So what that means is we have to change this stuff so that we're negating everything and forcing the outcome to be positive. So we could rewrite this as y equals 6 ln and now parentheses negative x plus 2, and then all that plus c. Or, if you wanted to be fancy, you could say 2 minus x inside here. For this problem, we want the particular solution to this differential equation satisfying this initial condition over here. So we'll start by taking the antiderivative. Antiderivative of 1 over x is going to be ln of absolute value of x plus c. So this is our general solution to this differential equation. But now we have to actually plug in the initial condition. So we have a y value of 3 that we're going to plug in over there for y. And that's going to equal ln of absolute value of this negative 1 x value that we're plugging in, plus c. ln of absolute value of negative 1 is really just ln of 1, which is 0. So we end up with c equaling 3. Now we're going to plug that back in here, but we can't have an absolute value in our final answer. So we're going to take a look at our initial condition. If x equals negative 1, if this inside stuff equals negative 1, that means the inside stuff's going to be negative in general. So that means we have to change this so that we're forcing it to be positive by negating the stuff inside the ln. So I'm going to write this as y equals ln of parentheses negative x, and then I'll add the plus 3 on the end there. On this problem, we want the particular solution for this differential equation going through this initial condition. So first, let's start with our antiderivative. That's going to be x squared plus x plus c, y equaling all that. Now we plug in our initial condition to figure out that c value. So I have a y value over here of negative 2, and then I'm plugging this negative 1 x value in here and here, so we have negative 1 squared minus 1 plus c. Well, this is really just 1 minus 1 plus c, so that's just 0 plus c, which means that c equals negative 2. And then we can just plug that back in up here, so y equals x squared plus x minus 2 is our final answer on this one. For this problem, I want the particular solution to this differential equation with this initial condition over here. That's a pretty wacky looking y value there. All right, so let's start with our general solution by taking the antiderivative of our differential equation. So we can write y equals negative 3 ln absolute value of x plus 1 plus c. Now we have to plug in our initial condition. So all of this craziness over here is just the y value. And then this 3, this is the x value that we're plugging in inside this absolute value. So this stuff equals negative 3 ln of 3 plus 1 plus c. So this is really just negative 3 ln of 4. If we add that over to this side to get c by itself, it's going to cancel this negative 3 ln of 4. So we just end up with c equals 3. And now we're about to plug that back in. But before we do that, we have to get rid of this absolute value. We can't have that kind of ambiguity in our final answer. So that means we have to figure out, should I just drop the absolute value or negate everything inside? With our initial condition, we have an x value here of 3 that we're plugging in. So if x equals 3, this x plus 1 stuff inside absolute value is going to come out positive. That means that I can just replace the absolute value with simple parentheses. So I can then write y equals negative 3 ln of just parentheses x plus 1. And then don't forget to actually do the plus 3 on the end there. On this problem, we want to know which of the following is the solution to this differential equation, 2 sine of x, with this initial condition over here. So one way to do it is to just take derivatives and see which one gives you this for a derivative and also equals 1 when you plug in pi. Certainly one way to do it. Another way to do it is to actually do the differential dance here. Start with the antiderivative of 2 sine of x, which is y equals negative 2 cosine of x plus c. And then we can plug in our initial condition to find the missing c value. So we have a y value here of the 1 that this stuff equals. And then we'll do negative 2 cosine of pi. That's the x value we're plugging in. And don't forget the plus c has to stick around there. So what's cosine of pi? Well, that's negative 1 times negative 2 is 2. So we have 1 equals 2 plus c. Subtracting that 2, we have c equals negative 1. So plugging that back in, we can write y equals negative 2 cosine of x minus 1, which is going to match up with answer choice E. For this problem, they're telling us on the graph of f, the slope at any point is twice the value of x. We've got this f of 2 equals 3 value here, and we want the value of f of 3. Okay, so they're essentially giving us a differential equation in disguise. If we write the slope at any point, well, we could just call that dy over dx, and is twice the value of x literally means equals 2x. So we can write dy over dx equals 2x. That's what this means symbolically. And they're also giving us an initial condition, essentially. So let's do the differential equation dance on this one. We'll start by taking our antiderivative to find the general solution to this. So this is just going to be x squared plus c, y equals that. And now we have to plug in this initial condition of the point essentially 2 comma 3. So we have a y value of 3, and then that means we have 2 squared plus c on the other side. Well, this is just 4 plus c, so subtracting that, we get a c value of negative 1. So plugging that back in, our equation, our actual equation on this is y equals x squared minus 1. And at this point, we can just plug in 3 for x and figure out the y value. So that's going to be 3 squared minus 1, which is just 8. Choice C. For this problem, we're given that y equals f of x is a solution to this differential equation with this initial condition. We want to know the original function. Now, normally the way we would start one of these is taking the antiderivative of the differential equation, getting your general solution, plugging in your initial condition to get the c value, and then you should end up with one of these answers or something close to it. However, that's a little tricky here because we don't really know how to find the antiderivative of e to the x squared. Substitution's not going to work, and integration by parts, maybe it would work, who even knows. This would be definitely a nasty one to attempt. So it's actually going to be faster on this problem to just test out all of these answer choices until we find one that meets both of these two conditions. And if you think about it, these aren't too tough to test, right? We just have to take the derivative of each of these to get this thing. And if, the ones that actually pass that test, we can plug 0 in to see if they actually give us 2. So let's start with answer choice A. We'll do the derivative of this thing. So let's see, if I take that derivative, that's going to be e to the x squared times a tail of 2x. So 2x times e to the x squared. That's not the same as what they gave us up here, so we can eliminate that one. On to the next answer choice. Taking the derivative of this thing, we could do it. It's going to require the product rule. We could do it fairly quickly, but it's even faster if we just plug in 0 right away, because you've got 2 times 0 times the rest of this. We see here that f of 0 is going to equal 0 on this one, which means that it also cannot be our answer, because f of 0 is supposed to equal 2. Moving on to the next one. Derivative of this, since you're taking the derivative of an integral that has an x in the upper limit, this would just come out to e to the x squared, which is exactly what we want. However, if you try to plug 0 in for x, this would require us to find the antiderivative of e to the t squared, plug in 0 and 1, and I'm not even sure, again, how to find the antiderivative of that. That was our issue up here. So we're going to go ahead and, table this one. So maybe this one is true, but we're not really sure about the whole f of 0 part. We'll come back to it if there's not a better answer choice. Moving on to this next one. The derivative of this one, the 2 gets differentiated away. You've got e to the x squared for this other piece. So that part checks out. And this time when you plug in 0 for x, f of 0, this is going to be an empty integral. You're integrating from 0 to 0, same limits of integration. So this whole integral is going to come out to 0 whether or not you know how to take the antiderivative of the integrand here. So you just have 2 plus 0 then, which comes out to 2. So this one actually meets both conditions, and it's looking like a pretty good answer choice. Let's just quickly check this last one to see if it's even better somehow. Derivative of this one is going to be e to the x squared, so that checks out. But again, we don't know how to take the antiderivative of e to the t squared, so we don't really know how to evaluate an integral from 0 to 2. 0 to 0 we could do because they were the same number. 0 to 2, not so much. So it looks like the best answer choice then is going to be D. On this problem, they're telling us the points -1, -1, and 1, -5 are on a graph that satisfies this differential equation. So based off of this, we want to know what's got to be true out of all these. These are all talking about whether the original function has a local min or max or point of inflection. So definitely, we're going to need to run some derivative tests on this. In order to figure out really all of these, we're going to need the second derivative, certainly for the point of inflection, and also for finding the local mins and maxes, because it's going to be kind of hard to do first derivative sign analysis using something with 2 different types of variables in it. So let's get our second derivative out of this. So I'm going to say d squared y over dx squared equals 2x plus dy over dx. And now that I've got that, I'm going to run a couple tests on this first point here, -1, -1. So running my first derivative test on that, or at least just the first derivative to get that value, that's going to be -1 squared minus 1, which comes out to, well, that's just 0. So we definitely have some kind of critical value at this point. Is it a min or a max, or neither? Well, we need to plug -1, -1 into the second derivative for that. So that's going to be 2 times -1 for the x value. And then we're going to have plus 0 because we had a derivative of 0 at that point. So that ends up being -2. Now significantly, this is a negative number. Because we have a value of 0 for the first derivative and a negative second derivative, that means we're going to have a max at the point -1, -1. Okay, well, let's test out our other point here, 1, -5. So running the first derivative on that, that's going to be, let's see here, 1 squared plus -5. So that's -4. So that's not any kind of critical value for the first derivative. But it still might be possible that there's a point of inflection there. So let's run the second derivative just to be on the safe side. Now, taking a look at here, f has a local max at -1, -1. I mean, that's choice C, but we're just being really safe here doing all this other work. So second derivative, that's going to be 2 times 1. And then we're going to do plus -4, the derivative at 1, -5. So that comes out to -2, which is not 0, so there's no way there's a point of inflection there either. So there's nothing special happening at 1, -5. So then we can definitely confidently pick choice C, -1, -1 is a local max of f.